So I think today good thing is that we have some time, so we can go slow and we can have a lot of interactive conversations, right? And so there are really two parts to this. One is introduction to cache coherent interconnect, which is this has been industry effort, CCIX, and there are other efforts now, CXL, and we can talk about that as well if need be. But the key is to think about at least moving forward from PCIe, essentially, right? Enabling some new data sharing paradigms. There have been different efforts in the industry. C6 has been there now for some years. So first part is really introduction to C6. What really are the new use cases it enables? And the second part is really you can talk about some application scenarios that where we're concretizing this new technology. So some of the POC work that is happening, and as different pieces are coming together now, next year expectation would be that we have products as well. Okay. So this is I already covered. We'll talk about from use cases point of view. The topic that is probably of more interest here is really, connecting to persistent memory, that use case, and then also storage acceleration. So I'll touch upon those use cases. So the context of C6 was that really, I think you may have heard this in different ways. One is really that Moore's law is slowing down. So in terms of, anyway, doing everything in general purpose processors has never been very efficient. But because of the pace of innovation in processor space, it's been really easy to just utilizing processors, right? But now I think we're getting to a point where you don't get the natural benefit from year after year. So now there is more mind share to look for heterogeneous architectures, right? There have been efforts in industry for a number of years, right? But I think one can say it's gelling together now, right? So it's a matter of time, few years, that it will be not unusual to have another processing element in the system, right, in the host. You always had NIC and your storage, but intelligent processing near those interfaces and acceleration technology in the platform, right? And the drivers have been also, there's more demanding applications now, a lot more data to process. There is also increased focus on latency. 5G is driving that. So, essentially you're looking for optimal solutions to process data, and also solutions that can, do the processing it while maintaining low latency. So I think there is mind share towards this domain-specific architecture direction, heterogeneous architecture. And maybe one last point that I leave with this is that, so one way to think about it is that from software perspective, what does that mean? What is a good way to think about utilizing such a platform? So the idea is really here that, people are familiar with NUMA platforms. You can have large-scale NUMA systems. People know how to utilize, allocate data structures, processing near the memory, how to deal with some variations in latencies. So one way to think about it is that within a box you would have a little bit of a NUMA architecture, but at the same time the focus of these interconnects is to minimize the NUMA-ness, like the variation in latency you want to minimize, right? But still, to get maximum performance, you may want to be aware of that. So now a bit about C6 consortium. So this is a consortium that started in 2016. It's for 50 plus members. You can see, all processor vendors that are a member of this, except Intel. That's a very important thing. And now industry is coming together around CXL, while C6 is continuing to address some other use cases that are not covered by CXL, and C6 is here today. So this effort we started earlier on. It will continue to be relevant. It's here today, but now broadly industry will enable similar technologies. And we are part of CXL as well. So now specification wise, the work was done in 2018 when we first came together. Designs had already started, as you typically know that as the spec is happening, designs already get started. And now we already released 1.1 that supports Gen 5 speeds. Then we are releasing 1.2, which is focusing on some enhancements to protocol layer. It completes the picture on the protocol layer side. So essentially after 1.2, we believe that C6 is pretty complete, except that we can keep innovating in the basic file layer level, right? Maybe chip to chip. Our focus would be more like chip to chip interconnects. That will be one of the things we'll be focusing on. So now host-wise, today there is Huawei had announced earlier, but given the current situation, not everybody has access to Huawei platform as a host. ARM has a host platform, which is based on actual silicon, 7 nanometer silicon, which has their state-of-the-art processors in it. But this is not for purchasing as a product. It's more software enablement. So it has 4 cores in it, and it has all the IPs, C6 interconnect, but full Linux stack on it, right? And you can see it at ARM Tech on next week, week after. Yeah. Okay. So ARM. So basically today, on the endpoint side, and there are third-party, processors that would be coming out, I would say early next year. Oh really? Oh, I see. Sorry.
Just not looking at.
Oh, I'm sorry. So is that better? Little bit, or is it me? I don't know.
You can't wander.
Yes, I like to move around a bit, but it's okay. So, so I was saying is that some of the processors will be coming out, later, early next year. On the endpoint side, so to have the whole platform, you need a host with C6 capability, and C6 is cache coherent interconnect for accelerators, right? C6 capability, and then you need endpoints. Endpoint-wise, Xilinx endpoint has been there since 2017, latest 2017. And we have LVO card 280 today that supports C6 capability. And then our 7 nanometer part is now sampling that has full hardened support for C6. So essentially the point to audience here is that if somebody wants to try a use case, the platform exists today. The stack, the host, the endpoints, and we can, one can explore that. Now, software enablement also has happened. It's a work in progress a little bit, but mostly like, UFI work is done, and I'll talk more about that. So now, so first few slides, like 10 slides, I thought to give a kind of overview, so, we can go faster, slower. It's about the capabilities of this interconnect. And here, some people may be quite familiar with cache coherency concepts, but some audience may not be. So I just have a few slides to introduce the concept. So here, first aspect is, you talk about a requesting agent. A requesting agent, you can think of it as a processor core with L2 cache or L1, L2 cache with it. So it's an initiator of a request, and then request goes out. The cache, the data coming back can be cached in the cache. So that's the concept of requesting agent. So then it can keep a local copy of that access data, and if future access happens, it can reuse it. Unless, for some reason, it has to evict the data out. Either it has to evict because of its own capacity issues, or it has to evict because somebody else wants to modify the data, right? Otherwise, it can keep the copy locally. So this is a concept of a requesting agent. It's like a CPU with a L2 cache, right? Second is a home agent concept. So RA, requesting agents are RA. Home agent, we call it HA. This is a concept where you have multiple requesting agents. They are trying to go after some memory area. And a good way to think about it is that just focus on one cache line, which is 64 bytes typically. So multiple requesters are interested in one cache line. So home agent is the central unit where every request goes, right? And behind it is the memory that actually holds the data, right? And central home agent job really is to make sure that in presence of multiple copies of the data, right, that memory consistency is maintained, that really there is only one latest copy and everybody gets that latest view of the data, right? So it's like everybody is going to that request, the home agent, and he is arbitrating, like who gets to keep the copy in what state. Okay, that's home agent. Then there's a concept of slave agent, which is basically, as I said, so requester is going to a home agent, and home agent, if it decides where to get the data from, the data could have been in a cache of a requester, right? And if the data is modified in the cache of the requester, then home agent really doesn't have a choice but to get it from there, because that's where the latest copy is. But otherwise, it has a choice to get it from memory itself, because the latest copy also exists in a memory controller behind it. So every home agent has a portion of address range that it is homing, and essentially that address range is in a memory controller, right? So slave agent is this, where you are saying is that today, by default, these memory controllers are in the same SoC as the processor SoC, like the DIMMs connected, right? Memory controller followed by DIMM. What interconnects like C6 enable, and it's very important for persistent memory scenario also, storage class memory scenario also, because in this case, it's like a memory, which has its memory controller, but it may not be attached to processor SoC. If people are doing NVDIMM or similar interfaces where it would be attached to processor SoC, right? But that's not the only choice that is interesting. You want to be able to connect this over some interconnect, right? So in that scenario, basically you're saying is the home agent now can actually talk to a memory controller that is not locally connected through private interconnect, but over PCIe or C6 or something, right? So that's the notion of a slave agent. Slave agent is like a memory controller that can talk to a home agent, and it's across the C6 interconnect. Okay, just these three concepts, and the rest we can move forward. But like as we talk about how the capabilities come together, these were important three concepts. Any question at this point? Maybe I can keep it interactive also. If not, okay. So now what C6 did, right? Well, so we basically said that PCI is limiting, and we'll talk more about what the limitations are. Is the use model, is the bandwidth, is the latency, all of that, right? So first thing we said is that PCI has a lot of goodness, right? I mean, of course, a lot of solutions out there utilize PCI. We need to coexist with PCI. Secondly, PCI has this whole management solution that is already available, right? It's part of every operating system. The PCI management layer is part of operating systems, right? So you clearly want to leverage PCIe. So idea was that for C6, we take the PCIe as a transport, as a starting point, and then we make enhancements. So C6 transport is really the PCI transport as a carrier of the data, requesters and data, responses, but it is enhanced version of PCIe. And what is the enhancement? And I would love to go to the the slide there, but maybe yeah. So so here. So this is PCIe standard here, right? You have PHY, you have data link layer, and you have transport, right? The transaction layer. So this is the PCIe, the read writes happen here. There's a PCI packet that maps to some internal interface like XC or something. And the read write becomes a PCI packet, right? Inside here, and then it goes out, or data link layer, and then goes out. This is PCIe. So we said that we want to leverage this whole stack for management reasons and for legacy traffic. But for C6 traffic, for cache currency traffic, you want to have lower latency transport and a lower overhead transport, right? So way we did it is that we said that PCI already supports multiple virtual channels. Then instead of enhancing the transaction layer of PCI and intertwining new types of traffic here, we basically mandate that the PCI controllers now have two virtual channels implemented. From the PCI spec perspective, like there will be TC, like is a traffic class. One of the traffic classes is reserved for C6, and then the controller would implement, essentially get rid of the PCIe, and will define a new transaction layer, which is almost nothing. It's just a cut-through layer. And in this one, there's a mode here where we don't even care about really PCI header per se, right? It's just something arrives, and we just look at it, right? For a case when it's a point-to-point connection, we don't really need to worry about PCI header, except that we have to just worry about certain fields of PCIe. That's it, right? But here also we have a mode here where we can be PCI compliant mode. PCI has a vendor-defined format. It's like a vendor-defined message format, VDM. So we say that we can carry C6 as VDM messages. So this is very lightweight. It only carries PCI VDMs, if people are familiar with that, or our transition layer. So these are the enhancements we've done here at the transport layer. And then PCI data link layer is utilized as it is. There are no changes to that. And that really simplifies the ecosystem, because as a result of this, it's really very straightforward to enable PCI controllers to do this. And we did this without any area penalty, actually, in our designs. And C6 protocol layer is the protocol layer. We did a layered architecture where above this is like a coherent interconnect, where just like inside a processor, you have a coherent interconnect. You carry messages, requesters, response, so on, snoops. So that happens here, and then we bridge it over to this a packet that is going over this virtual channel. There are a lot more details, but it's not important probably right now. If any questions, I can address those. Okay. Now let's talk about use cases. This is a busy slide. We can spend some time, and then I talk a little more specific use cases. This is in one slide trying to capture in one slide I'm trying to capture enhancements that we have done over PCIe, right, from use cases point of view. So left side is the PCIe, and in PCIe, you know that PCI memory is private memory. You can do MMIO accesses to it, but by default, it's not cacheable memory. Processor cannot do a load store to this, right, and cache it locally. There is no home by default that is providing cache coherency for this memory. That's the PCI state, right? And second thing is that in PCIe, the usage model really is that it's a producer-consumer model, right? So PCI, you give some work request, and you have some pointers to some data buffers you give it. It makes copy locally, it operates on it, and gives the result back. It doesn't have a notion of, simultaneously, there is some intelligent thread running inside PCIe that is doing very active collaboration with a thread running on the processor, where you get the ownership of this data structure, where you're modifying the data structure, and as you do the modifications, it's visible to the other right side. And you can keep the local copies of that data structure. You can do it at a coarse grain level. You can take the ownership, operate on of the data structure, then flush out the data structure to the host side, and then pass on the ownership, right? You have to explicitly flush it out to the other side, essentially, right? And the CPU, so it's a slower process. Like you can make local copies, right? And then at some point in time when you're done, you flush it out, right? So PCI use case limitations. So in which ways we have enhanced it? So number one is straightforward is the vector above, which is memory expansion use case. It's not very hard to do, but at the same point, you have to do it in a standard way, right? What it's simply saying is that I have now a home agent in the processor that can home memory that is attached to the C6 interface, right? And you can cache it, any processor can access it, and then basically cache coherency will be maintained, right? And in this one, when you do a memory controller here, you just have to worry about few things. The things you have to worry about is that, you don't want to have deadlock scenarios happen, because if a requester comes from the PCIe, accessing its own local memory, is going up and coming down, you have to be careful that there's no deadlock scenario. And secondly is the home agent is fielding it. So by having a separate virtual channel for C6 traffic, we get rid of any kind of deadlock scenarios there, right? And also C6 is lower latency implementation, and that's a lot of it is implementation, some of it is architecture, right? So essentially it makes it a more suitable interconnect for memory expansion. Then you would have to do some custom crafting within PCIe and ask everybody to implement PCIe in a very performant way, right? For all, so on. So this is one, memory expansion. Second is data sharing model, as I was talking about. And here, the way to look at it is there are two vectors you can look at. One is this memory that we just spoke about. Where is the memory, system memory? That is, so when you talk about system memory, it's the memory that is managed by the operating system, not by the device driver, right? So there's also, you can have load store memory that is managed by device driver, which is okay. It's better than private memory, right? And what I call a load store memory is, as opposed to MMIO, load store memory is a memory that can be cached by the processor, right, natively. But that memory itself could be managed by a device driver or could be natively managed by the operating system, right, where it can page it out just like system memory, right, and so on. So first is that, so what C6 does it, that it expands the scope of system memory, right, from just not the processor attached, but also accelerator attached memory becomes part of system memory, right? So you have a terabyte here, you have 256 gigabyte here, your system memory that operating system can deal with is 1.25 terabyte, right? Okay. And then the other thing is the data sharing model, where again it's a coarse grain. Like let's say I own the data structure, I do multiple operations on it, I read it multiple times, I update it multiple times. In case of PCIe, I basically have to copy that whole data structure locally, modify it as much as I want to modify it, and at the end of it, I have to flush it out to the host, right? In case of PCIe. I mean, if you were only modifying one time, you could have just done a write to the host. That's fine, right? But the point of these data structures is that you may be working on it multiple times. So I basically will make a local copy. I do all the read writes to it as many times as I want, and then I will flush it out. That's the PCIe. While that's called coarse grain, right? Producer, consumer, one guy has the ownership and the other guy. Well, fine grain would be is that, basically I just, this one copy of the data structure, cache line basis is consistent, right? And I can do very fine grain sharing here, right, with the host. Okay. So if you look at this then 2 by 2, so in this quadrant, it's really PCIe, right? The PCIe, which is in coarse grain and host memory. That is what is today, right? But even for PCIe, we make some improvements. What we make improvement is that, as I said, we have this notion of lower latency transport. If you go via C6 and you maintain this same data sharing model as PCIe, you have more efficient bandwidth for small transfers, right? You have a lower latency because you will go over C6 interface, right? But you're not doing any new data sharing model. It's a producer-consumer model, but just a better transport, right? And then you also have a notion of aggregation, where today in PCIe, you just have one controller with certain number of lanes. You can have 8 lanes, 16 lanes, that's it, right? Or 4 lanes and so on. In case of C6, you have notion of aggregation, port aggregation. So you, for example, you have 2 controllers, each one is by 16. Upper layer of C6 will make it look like as if it's one controller from your point of view. So if you, not from management perspective, it's still 2 controllers from management. But if I do a load, right? That load, even addresses will go on one controller or will go to the other controller, and they will get reassembled correctly, and you just will get the data transfer done, right? So you can essentially have a very fat pipes with this way, right? So we have some improvements there. Then this is a case where memory is still in the host, but you are able to cache it. So you have a requesting agent that can be part of an accelerator now. It can cache host memory, do multiple accesses, and it's cache coherent. Home agent makes sure that everything is coherent, right? You don't have to do any flushing. The next one at the bottom here is that, let's go to the right first. So right one is when now the accelerator becomes a peer processor to the host. Typically you have this dual socket systems or multiple socket systems where they have private coherent interconnect between the 2 processor SoCs, right? And those private interconnect allow you to do fine grain sharing. Memory is here, it's part of system memory, and anybody can access anybody's memory. It's all coherent, right? So on. So C6 enables that paradigm where the home agent can be even on the accelerator side. It's not limited to be on the processor side, right? So if you put a home agent and a requesting agent on the accelerator side, it is really like a processor SoC, except it's not running general purpose processor threads. It may be running task-specific threads, right? And when we look at acceleration paradigms, you will see how we utilize that. It basically, now you can construct a paradigm where you have general purpose processor is one SoC, and task-specific computation engines or threads in the other SoC, and the data sharing model is as if they are all multi-core sitting in the one processor, right? Data sharing paradigm does not change. Because you have that coherent interconnect between the two SoCs, right? And coming to the bottom here is an optimization of the above case where you don't have a home agent locally, you have a slave agent and a requesting agent. So here you let the home agent be only in the host, but you do an optimization that if I'm going to my local memory, then I don't have to go through the home. It's a very detailed coherency level conversation, so I'll skip it, but essentially an optimized access to the local memory without having a home agent there. So you can enable some paradigms of near memory processing without having a local home agent. So these are all the use cases that C6 enables. Additionally, we'll map it to actual implementation scenarios. So next. So now this is one example where these comes together, and we did some demo. We're showing you different pieces of it. In SC18 we did a demo, then we did in ISC 18, then SC18. We did 2 demos, right? So this is a kind of a pattern. Like one can decide whether this is from the application perspective. One comes up with a design point that completely suits this, but at least it's a pattern of data sharing that is interesting. Okay, and it's simple to explain this pattern, right? So today, what you have is, if you think about KVS, a key value store, which basically you get requests where you get a key and then you do a hash table lookup. You have a pointer to where the value is, right? It's a very simple. Redis is an example of this. Memcached is an example. It's used broadly, caching layer. So in this case today, all of the processing, request processing happens on the host, right? Memory is in the host. So the values are in the memory of the host, right? And there's a hash table that is also in the host. So you basically do this metadata, hash table, let's call it metadata. You do that metadata lookup, which gives you a pointer, and then you read the value. So this is the starting point, right? Today. So if you now map it to the C6 capabilities and how this use case expands, right? Let me go bottom here first, down, and then it'll come up and then come down like this. So here, first example can be that for my value, if I just want to have much larger memory, right? So I would want to expand my memory. I would like to go beyond the memory that I can attach to the processor, right? I can now attach memory to a device, through a device that's connected over C6 interconnect. And C6 is really this enhanced PCI interconnect. So now I can have terabyte level of memory, particularly we use with storage class memory, there's an additional benefit, right? But if I just augment the memory there, I have all the application is still running on the host, hash table lookups happens in the host, request parsing happens there, but the value pointer points to memory on the accelerator. So you have to be a little tolerant to little longer latency if there is a latency, but people are working towards implementations where the difference between the latency seen on the host versus on the accelerator is minimized, right? If you get to the paradigm where that latency is truly minimized, then it's basically, from processor point of view, the value can be allocated to this expansion memory. So this is the one pattern, right? Then secondly, if it's a persistent memory, then it has even additional benefit, and I'll talk about it later, where now you naturally get the persistence, right, basically directly. You don't have to have this notion of, to get persistence, I have to periodically write it to a SSD, right? And I have to then have the checkpointing concept and so on. It basically instantaneous because you just store here value. So this is one benefit that happens. And this applies to many other scenarios, it's a pattern, right? Second is that now I could actually do, networking initially you still do, let's say, on the host because people have their own choice of networking card. But, and the get operations, delete operations, sorry, not the get, but the put operations, they are not very frequent. The write operations are not very frequent. the delete operations are not frequent, or any kind of replication, any things you do, all the intelligence you want to leave on the host. Because bringing it on Accelerator is more challenging because it could be all custom code, right? But the get operation is really simple. It just is doing hash lookup and getting a pointer, reading the data back, and going to the networking stack to send it out, right? So, but the get operations are the operations that happen very frequently, 97% of the time, 98% of the time. So one paradigm could be that I could offload get operation to the accelerator. And now, even though if I had a longer latency to this persistent memory, right, because my get are happening near memory and it's happening in the specialized hardware like FPGA or some other solution, I can be latency tolerant, right? So one paradigm would be, again, what CCIX would enable is to do some amount of near memory processing. And this pattern, the get operation could be offloaded here, right? I could do multi-get operations. I could do get operations which return very small amount of data. So you're not IOPs bound. You basically truly become the CPU bound or the networking interface bound. You are not really, your IOPs are not bound because what I mean is that you're really networking interface bound and not the CPU bound because you're offloaded the CPU here, okay? Now, in this, when you do the get operation offload here, there's a common data structure between operations that are happening on the host and the one in Accelerator, which is the hash table lookups, right? Host is updating the hash table, the linked list with the hash table, and this get operation is walking through that linked list, looking at it. Clearly, one could come up with a solution here because a simpler example. You could come up with a solution where I will come up with a way. I've taken this much time already. Amazing. It's only 10 minutes left. I have to pick up the pace. Wow, amazing. Okay. Sorry. Okay, but if you understand this pattern, that is already pretty good progress, and I'll go through really fast after that. So here, now, but what CCIX does is that you can just have one copy of this whole data structure. Hash table can be just in the host memory or local memory, but doesn't matter. It's very simple porting effort, relatively, as opposed to trying to create two copies of it, keeping them consistent, and so on, right? And then in the end, is saying is you can have a home agent also come in here, and if you brought home agent also here, then in that case, you are even more optimized because get operations are the one that do most of the accesses. Okay. CCIX enables flexible topology. This is one additional thing it does beyond CCIX, PCIe. PCI is a tree hierarchy. Here you can create a 2D mesh or fully connected mesh, and the routing layer is at a above layer than PCIe. Okay. And software enablement work is making good progress. It required exposing this memory that is accelerator attached as a different type of a memory to the host. It is a normal memory because it can be cached, but at the same time, you don't want operating system to allocate its own data structures into this memory. So we introduced this concept of called specific purpose memory. So if you look at UEFI now, I think it should be public. I think so. It's a specific purpose memory. Maybe there are already open source patches on this, so you would know this, right? We worked with even in Intel, we collaborated with them on this, and then other enhancement to ACPI, the RAS framework, all of that work is making good progress. Okay, and ARM's NUMA allocation, NUMA seeing this as a NUMA node, all that work is happening. So now I'm jumping into the use cases, but because you already got good background on the use cases, one pattern, it'll be really easier now to walk through this. So one is this memory expansion that I already talked about, which we showcased in SC18, where essentially we had the NUMA allocated in a host processor, and we showcased that how our values were stored in this device attached memory, right? And the hash table was shared. And we had shown in another conference a demo where get operations were getting done in the accelerator, right? So we had shown these two pieces separately. Now let's talk about persistent memory. Also, again, we can go faster because we already talked about this to a degree. I mean, I think so persistent memory is very, very, central focus, at this conference. And as you know, this persistent memory One paradigm, there are many paradigms to use it, right? One is totally application transparent way, that is different, but one is application aware way, and there you have this PMDK framework, where still PMDK framework is, it's more like a driver managed or PMDK framework, managed memory, where it is exposing you some interfaces. Maybe it is a key KVS interface it's exposing. So it's the PMDK layer that is doing load stores directly on this, not the application going through an interface. But you're getting the benefit of it being a load store because the PMDK interface doesn't require any OS calls at that level, right? I mean, it can directly just control this memory, right? Access this memory as a load store, as cacheable memory, and so on. Then, of course, you can also have this natively exposed, and you can use it as you see fit. I mean, this memory, persistent memory, you can just be part of system memory, and you deal with the reboot problem at some level, and but it's just a system memory which is persistent, or you can just use it as a volatile memory. It's up to you in your application. So all that we already discussed, and this enables. And this is just showcasing, and if people are interested, there is an ARM TechCon that is also in Silicon Valley, the conference, which is October 8th and 9th. And there the plan is to showcase this proof of concept or this demo, where they've taken a Redis example. And in case of Redis, today the default is that periodically updates happening, the put operations happen, you put the new values in system memory, then you periodically, you're checkpointing, right, periodically. So you create the log here, and you're starting to flush the log to persistent memory, and then you periodically do the checkpointing to the disk, right, today, or SSD. And this is a slow process. It takes a certain amount of performance. And also to rebuild it then takes some time when you have to restart in case of system being down. But with persistent memory, this becomes basically a direct process. Like the values are always written in persistent memory, not in the host memory, and then periodically checkpointed to the persistent memory. Okay. But if you have to go to remote memory, that's a different problem. But usually in these scenarios, anyway, you're not dealing with the primary storage, you're dealing with the cache layer. And it's all local, right? So now other demo that we are doing in SC19 is we are doing storage layer acceleration for MongoDB. And we are looking at specifically White Tiger. And maybe I'll quickly go. So what happens there is, what happens is that so you get these updates, document updates you're getting, and they are in your system memory. And at some point in time, when you're running low on memory, your system memory, right, you would be flushing them out to persistent storage or to disk, right? And this is through the White Tiger is one of the engines. There are other engines also. But in this case, periodically there is a hiccup that happens where you are talking to this persistent storage, right, to flush this data out. So this is one of the observations we have. Secondly, the IOPs are typically anyway limited because all of the file writing is happening on the host. So both of these things, increasing the IOPs generally, and also minimizing these pauses, the hiccups, where you are flushing this data out, is what we want to strive for. And then there's one added angle is that sometimes when you're pushing it to the persistent memory, then you want to also do compression, right? And you may want to do encryption also, but at least compression. Then if you, at the point of flushing, you introduce compression further, then it's even worse, right? And what we want to be able to do that is that even do that without penalty, right? So the way we are doing it is that I was going to just very quickly show, but essentially what you're doing is that ultimately you're writing into a file system. When you're writing to this persistent memory, it's a write to a file system, right? So this concept goes beyond just doing it in the context of White Tiger. Idea is to really do accelerated implementation of a file system, right? And how do we do the accelerator implementation? There's very complex, metadata structures involved in this, right? There is inode structures, then there are these bitmaps that tell you on the block where are these inodes, where are the datas, right? And there's a super block which keeps some other information around, access rights and so on. So the point is that in this application, the KVS had a simpler shared metadata, which was a hash table which had linked lists. Here is complex metadata, right? In case of KVS, you could have thought about that I don't really need metadata sharing between the two sides in a fine-grained fashion. I could make it 2 copies and somehow keep them consistent periodically. Here it will be very challenging, right? So people have done very proprietary solutions in past to do this accelerated file systems in hardware. What we are trying to show here is that how it can be done much more easily and become more mainstream, right? So in this case, we basically are saying is, so maybe the architecture I'm going to show is in the interest of time, the control commands, all the control commands stay on the host, right? Only the reads and writes are offloaded, right? Between all the control structures and read writes, there are shared metadata. They stay just 1 copy of the metadata, right? And both sides can access it, update it coherently, right? So and you can realize it in many different ways. So this is one example you can realize it in, that basically from the application point of view, you don't even go into kernel, right? You just have a library, user space library, and you just come to FPGA, let's call it, or Accelerator, which is implementing file system. So you just come here directly from the application, right? And this is a trusted environment here in the Accelerator, right? This is the one that does the privilege checks it needs to do, right? And if it is, it can also implement all of and the management interface some of the interfaces can go through the kernel, right? The management interfaces can also go through kernel. But the read writes can come here directly, right? And there's shared metadata, which could be either in the host memory or could be local. So in this fashion, and then you can do compound operations here. You can say that I want to do a write with compression or read with decompression. The point here is that what helps here really is that because in the Accelerator and FPGA, you can think of it as that I can do a very parallel implementation. I can do custom implementation of the storage layer, right? I can have as many threads as I want. I can have an array of processors. It's not limited to be standard Linux environment fully, right? It could be Linux environment, right? It could be I can design it whichever way I want, right? While all the complex operations or any other applications like replication, anything else that's running, you could still be running them on the host if you want, because the metadata is really same on the both sides. Okay? So there are different ways to realize is that, one is split as this, second is split as the metadata could have been on the FPGA side. Third is that I could have done, the first layer of the file system, which takes a read-write request and just takes it all the way to the block cache. That I could do in the host. And it's only taking the block cache to the block IO I could offload to FPGA, right? That's another split one can do. I think so. This is the last slide I have. Is point of POCs are on the way. One is the PMDK NAM TechCon. Then we have this SC19. We are doing MongoDB acceleration and memory expansion. We are showcasing on our 700 part. And this is a summary slide. Right. Any questions I can take or? Okay, then thank you. Yeah.